Okay, ladies and gentlemen, hope you're all doing well and hope that this video lesson will help. Today, we're going to continue talking about using scientific measurements. Today, we're going to bond a little bit in accuracy and precision, and we're going to talk about significant figures and some of the rules that are used when working with significant figures. So, with that in mind, ladies and gentlemen, I'm going to get started real quick. I'm going to start sharing my whiteboard in a minute. And hopefully, this will help you guys. So, the pages that we discussed today are pages 44 through 46 of your textbook and section 2.3. So the topic for this video is going to be significant figures. All right. But before we get into significant figures, let's talk a little bit about errors in measurements. And one of the things that we need to understand, it says some error or uncertainty always exists in any measurement. So there's always going to be a degree of uncertainty in every measurement that you take. It says, and then this is pretty important. It says the skill of the measurement places limits on the reliability of the results. Okay, so the skill of the measure places of the measure places skill of the measure places limits on the reliability of the results. Reliability of the result. And what this statement means or is trying to say is that basically the skill, how well someone knows how to use an instrument will always limit the reliability of the results. There's always that error when someone is using any type of instrument, especially in chemistry, which is, sometimes it can be tricky, especially if you're working with certain chemical reactions. The other thing, it says that conditions of measurement also affect the outcome. So the conditions of the measurement also affect the outcome. And what that means is that there's always some sort of environmental condition. There's always something that could possibly or probably affect the result of the measurement. That's why in science, there's never always a 100% certainty that that's exactly how it's going to go. In fact, um, the reality is that scientists always try to avoid giving any absolutes because of these types of errors. The person using the instrument or something in the environment or other factors that could have possibly affected the result. But what scientists do have is I guess, an average, or they try to base it on the most consistent result. It's, for example, in hurricane season, which we're currently undergoing here in the Caribbean, when a model or a trajectory model for a cyclonic system appears, there's never 100% that's the way it's going to go, but based on what all the other models show is how meteorologists in this case make a possible or a probable trajectory for the system. But they always try to avoid any absolutes just because, unfortunately, that's not always possible. It says when you use a properly calibrated measuring device, you can be almost certain of a particular number of digits in a reading. So let me go ahead and type that up for you guys. It says when you use a properly calibrated measure, when you use a calibrated, properly calibrated measuring device, you can be, or it says you can be almost certain you can be almost certain of a particular number of digits. A particular number of digits in a reading. Of a particular number of digits in a reading. Okay? Of a particular number of digits in a reading. So what this is saying is that if the instrument is correctly calibrated, there is a very slow chance or very low chance of there being errors. It's not that they're going to be completely eliminated, but it gives you a less of a probability that you have any sort of errors. Okay, so we're going to continue now to avoid errors. What scientists have or have come up with is something that we call significant digits or significant figures. In some books, like I said this morning in class, they can be called Sig Figs. So let me just type up real quick the definition that your textbook gives you in terms of significant figures, and hopefully that will help out. It says significant figures in a measurement consist of all digits. So a significant figure consists of all the digits known with certainty. Digits known with certainty known with certainty and or plus one final digit which is somewhat uncertain plus one final digit which is somewhat uncertain, or is estimated. So in a significant digit, and we're going to talk about rounding in our next video lesson, but a significant digit, there's always numbers that are certain, but there's always one number that is estimated or rounded, right? We're not going to say rounded because rounded has another series of rules, but always estimated. So there's always those digits that are for sure. There's always going to be one that's going to be estimated. So that's what a significant figure is. Now, another important thing when we're talking about significant figures or significant digit is that the term significant digit does not always mean certain. So significant digits is not or does not mean certain. That sounds better. Does not mean certain. So just because they're significant doesn't mean that they're certain, because sometimes a significant figure is estimated because it's between two digits, but you can't really tell which one it is. So you estimate it. So significant digits are not always certain. A couple of the first couple of digits are pretty much known, but there's always that one digit that's not really certain. And another thing is that in any correctly reported measure, the final digit is significant but not certain. In any correctly reported measured value, the final digit is significant but not certain. So in any correctly reported measurement that has been estimated, the the final digit is significant but not certain. So there's always that degree of estimation. And again, in science, there's no absolutes. Um, so significant digits. So when we talk about significant digits, if there are some rules that pertain to the significant figures or significant digits, which is what we're going to go over now. So I'm actually going to go ahead and clear the whiteboard, and we're going to start working with the rules for the significant digits. So give me one sec while I retrieve the file. Um, and we're going to talk about some of the rules that are involved in significant uh, figures. So the first rule that we're going to see says that zeros between non-zero digits are significant. So let me type that up. Zeros between, or appearing between, excuse me, appearing between non-zero digits are significant. For example, if we have 40.7 and we have 87.009, these are significant because those zeros are actually located between non-zero digits. For example, the in the case of the 40.7, the zero is between the 4 and the 7. And in the case of the 87.009, the zeros are between the 7 and the 9. So as long as I have a zero between two numbers that are not zero, that means that they're significant. So that would be rule number one. Rule number two, which is in your textbooks. So rule number two says rule number two says that zeros appearing in front of all non-zero digits are not significant. Zeros appearing between, or not between, excuse me, in front of all non-zero digits all non-zero digits are not significant. And what that means is that all zeros to the left are not significant. So if we have 0.095897, 95897, 0.095897, this has five significant figures because the zeros that are in front of it don't count. So if you look at the zero here, and let me, I think I wrote a comma there. Excuse me. Let me. In some countries that's accepted, but not in ours. So, anyway, all the zeros to the left of a measurement are not significant. Likewise, if we have 0.0009, all the zeros in front of that are not significant. So that means that there's only one significant figure here. Now let's go to rule number three. Rule number three says, and then soon we'll see an example, zeros at the end of a number to the right, at the end of a number to the right, zeros at the end of a number to the right of a decimal point are significant. Are significant. Okay, are significant. So, um, real quick, what that means is if I have zeros that are to the right of a decimal point, like 85.00 grams, just to, I'm sorry, those are old, 0.00 grams, has four significant figures because the zeros to the right of a decimal point here are considered significant. Likewise, if we have 9.0000000000, this one millimeters, let me give it the measurement millimeters, because remember we're working with measurements, so millimeters. Let's see if I can bring this down a little bit here. Millimeters has 10 significant digits because as long as the zeros are to the right of the decimal, we consider them significant. So it's kind of like the opposite of number two. Number two says that all the zeros to the left of the decimal point are not significant, and the third rule basically says all the zeros to the right are significant. Rule number four. Rule number four. It sounds like a mouthful, but all it's trying to say, excuse me for that, all it's trying to say is that if I have a number or a measurement, I'm going to paraphrase it, I'm not going to write it exactly what's in the book, but if a measurement has zeros and no decimal point, at the end of the measurement, the zeros are not, may or may not be significant. May or may not be significant. Okay? May or may not be significant. And that's kind of summarizing. Now, this is what I mean. For the purposes of our class and the textbook that we're using, if I give you a measurement like 2,000 meters, but there is no decimal point at the end of that last zero, we simply say this has one significant figure, digit or figure. Okay, so it only has one significant digit because at the end of the last zero here, let me make some space. At that last zero, there is no decimal point. So for the purposes of our class and the textbook that we're using, we're going to assume that that has only one significant figure. However, in the opposite case where I say, or I give you the same measurement, move this over here, I give you the same measurement and I say 2,000 meters, excuse me, 2,000 meters, but there's a decimal point at the end. The decimal point is right there. This decimal point means that the zeros in that measurement are significant. So we say that this one has four significant figures. And we're going to see an example right now, but I just want to review this with you guys real quick. So again, rule number one, basically zeros appearing between non-zero digits are significant. So This one, 40.7, has 3 significant figures, and 87.009 has 5 significant figures because the zeros are between, in this case, 7 and 9, and in the case of the 40.7, the zero is between 4 and 7. The second rule states that zeros appearing in front of all non-zero digits are not significant. So for example, 0.095897, these two zeros here are not significant. We only count from the 95897, and this figure has 5 significant digits. So this one has 5 significant figures. This one has 3 because we said that the 0 is between the 4 and the 7. And in the 87.009, this has 5 significant figures because the zeros are between 7 and 9. So again, going to rule number 2, all zeros to the left are not significant. Okay, so these two zeros are not significant, and if I count from 95897, there are 5 significant figures. If we look at the other measurement, it says 0.0009. All the zeros to the left of the 9 are not significant, so we say, or we conclude, that there is one significant figure in this measurement right here, and I'm talking about this one. Okay. Now, if we look at rule number 3 says zeros at the end of a number to the right of a decimal point are significant. So since these two zeros are to the right of this decimal point, we simply say that there are 4 significant figures in this one. If we look at 9.00000000 millimeters, because the zeros are to the right of the decimal point, which are right here, we say that this has 10 significant figures. And our last rule, rule number 4, which pertains to this textbook, basically it's saying that if I give you a measurement and in the last zero, there is no decimal point. Like there's no decimal point in our first measurement that says 2,000 meters. So we assume that these zeros are not significant, and we say that there's only one significant digit or one significant figure. If we look at the second measurement, at the end of the last zero in the 2,000 meters, there is a decimal point. And because there is a decimal point, we include the zeros in our answer, and we assume that there are 4 significant figures. So that's pretty much it. Now I'm going to give you an example, which is the sample problem D in your textbooks, and we're going to go over that real quick. So if we look at sample problem D, and again, I'm going to erase all this. Sample problem D says A, 26 or 28.6 grams. Because there are no zeros here, we see that there are 3 significant figures in this one. And I'm just going to go ahead and say Sig Figs to abbreviate it, but there are 3 significant figures. 3 significant figures. If we look at the second one, let me do something real quick. That 1 is not part of the answer. Sorry about that. 28.6 has 3 significant figures. If we look at our second figure, it says 3,440. 3,440, but there's a decimal place in the last zero, decimal point in the last zero, and it's 3,440 centimeters. Because there is a decimal point in the last zero, we say that we include that zero as a significant figure, and we say that there are 4 significant figures in that particular measurement. Okay, 4 significant figures. If we look at C, it says 910 meters, but notice the 910 meters has no decimal point at the end of the last zero, so we only say that there are 2 significant figures in that one specifically. two significant figures. If we look at D, says 0.04604, 4,000 or 4604, or how you guys want to say it, liters. Now this one, we see more than one rule being used because the zeros to the left indicate that that these zeros are not significant, but the zero that's between the 6 and the 4 is significant. So we say that this figure has four significant figures or four significant digits because the zeros to the left don't count, but because there is a zero between the 6 and the 4, we say that there are four significant figures. And in our last one, it says 0.0067, and we have three zeros after the 7, so 000 kilograms. Now this one, again, we have more than one rule being applied because the first rule says that the zeros to the left, or the first thing we see, excuse me, is that the zeros to the left are not significant. So these three zeros here are not significant. And then we have 6, 7, and three zeros after the 7. Now, the third rule says that the last three zeros are significant because they are to the right of the decimal point. So 0.0, these zeros don't count, but these three zeros do because they're to the right of the decimal point. So we say that that one has five significant figures, okay? Five significant figures. So it is just a thing of just kind of reviewing these rules, knowing how to apply them. This sample problem is on page 4, or this example is on page 46. Above that sample problem, is the table with the rules that I explained previously in the video. Your assignment is on the LMS. All you guys are going to do is the sample problem 1 on page 46. So guys, I hope this video was helpful, and I will see you guys in our next class. So stay safe.